Okay, so now let's come to the next station in our journey, which is we wanted to compute the gradients with respect to the hidden units, right? So again, following this outline, so we are done with this part, right? And now we want to talk to the hidden units. And remember, there could be many hidden layers, right? But I want to come up with a generic formula so that irrespective of whether I'm in hidden layer 1, 2, 3, 4, it doesn't matter. I should have a similar formula or a similar set of computation, right? I don't want to derive this formula independently for every layer, right? The output layer was spatial, so I'm okay with deriving a formula for that, but I don't want to do it for every hidden layer, right? So that's what we'll focus on. Okay, so let's start. So before that, right? So let's try to see what we are, where we are headed, right? So this is our hidden layer. Okay, this is the activation at the hidden layer, right? So in particular, this is say H to 2 because it's the second hidden layer and the second neuron in the second hidden layer, right? And I want to take the derivative of the loss function with respect to H to 2, and what this diagram is saying that there are multiple paths from the loss function to this H to 2, right? That's what it is saying, and there is some significance of that. So what we'll try to do, right? Now suppose I have a variable z, okay, and I compute say one function of z, right, and let me call the function as q1, and suppose q1 of z is just z square. Okay, so I compute that. So I have computed q1 of z from z. Similarly, I say have another function, right, say q2 of z, let that be z cube, and I have computed that also from z, right. And then let me have say q3 of z, which is equal to e raised to z, right. So all of these are functions of z, and then say using these three as inputs, I am computing some p, okay, and suppose that p is just say q1 divided by q2. I'm just not writing the of z in the bracket, right, just to avoid, I mean, this is just cumbersome to write, right. And now is p a function of z? Yes, it is a function of z. Why? Because q1 is a function of z, q2 is a function of z, q3 is a function of z. So this p is also a function of z because it has been computed using quantities which in turn were computed using z, right. So I have this kind of a situation. So now I can I ask the question, can I ask you to compute the derivative of p of z with respect to z? What do I mean by that? Would this derivative exist, like, or would it just be 0? The derivative would exist, right, because I just said that p of z is a function of z, right, because it is computed using quantities which in turn depend on z, right. So this question is a valid question. Now how will you compute this derivative? This derivative would simply be the derivative of p, right. I'm just going to use shortcuts now with respect to q1 into the derivative of q1 with respect to z plus the derivative of p with respect to q2 into the derivative of q2 with respect to z plus the derivative of p with respect to q3 into the derivative of q3 with respect to z, right. So what am I telling you? I am going to sum the derivatives along these three paths, right. I am just going to apply the chain rule along these three paths and then sum the derivatives, right. So that's what you do when you have this kind of a situation. This is just from basic calculus. I have just revised that, and now I'll just write this as a more compact formula, right. So this is the formula that I would write, that if I want to compute the derivative of p of z with z such that there are multiple paths, right, there could be as many, right, so such m paths such that I have z, I am computing some intermediate quantities q1, q2 up to qm using this z, then if I want to compute the derivative of p with respect to z, then it would be p with respect to q1 into q1 with respect to z plus p with respect to q2 into derivative of q2 with respect to z, and I am just going to sum all these paths. That means there are m such paths, and I am going to sum the chain rule across each of these paths, right. And in any one path, the chain rule, this is what the chain rule looks like. It's a product of these two quantities, which is derivative of p with respect to q and then derivative of q with respect to z, right. So that's what it looks like. Straightforward. This is what you know already from calculus. I'll just quickly revise that, right. And that's exactly the kind of situation that we have here. you have this quantity h22, you are interested in the derivative of the loss with respect to h22. You know that the loss depends on h22 because it depends on quantities which were computed using h22, right, which depended on h22. So the loss depends on h22 and there are multiple paths. How many paths are there? There are k paths here, right, because from h22 you go to a31, okay, and from a31 you can go to the loss, a32 you go to the loss, because the loss depends on a31, a32 all the way up to a3k. All of this the loss depends on, and all of these in turn depend on h22. So there are k paths from h22 to the loss function. So if I want to compute the derivative of the loss function with respect to h22, I'll have to sum across these k paths, right. So in my case, the p of z is the loss function. My z is equal to hij. I took a specific h22, but it's in general hij. And my intermediate outputs are these ALMs, right. So AL1, AL2, AL3 and so on, those were my intermediate outputs, right. Okay. So with that, let's try to see how to find the derivative. So again, we are interested in the derivative of the loss function or the gradient of the loss function with respect to h2. Remember, h2 is a vector, but I won't go to the vector directly. I'll focus on one element of this, maybe h22, and in general I'm just going to call it as ij, right, where I is the layer number and j is the neuron number, right, neuron number in that layer. Okay, let's remember that. So that is the setup, and based on the formula that I had, there are k paths which take me from an hij to the loss function. Okay, so I'm going to sum over all those k paths, and each path I'll have this chain rule which I'm going to compute and sum over those chain rules. And what is the chain rule saying? Derivative of the loss function with the a unit in the next layer, right. So I want I. So in the next layer, the a neuron in the next layer depends on the h neuron in this layer. So that's ai plus 1, okay, and there are k of those, so I'll sum over m to 1 to k, and then the derivative of that with respect to hij, right. And I'm confidently doing this because just on the previous lecture or the previous video, I have actually shown you how to compute the derivative of the loss function with respect to a3. So I already have this quantity, right. So I am happy that this quantity is in the path because that quantity I have already computed. Okay. So let's go ahead. So as I just said, this quantity I have already computed in the previous video, right. You can see that we had computed the partial derivative of the loss function with respect to every neuron in the output layer, right, A31, A32 all the way up to A3k. So this quantity I have already computed, right. Here 3 is equal to I plus 1 and these are the m. So this I have already computed, right. What I didn't know was this, right. So what is this saying? Let's see. I want to compute the derivative of one of these guys, okay, with respect to one of these guys. That's what I want to do, and I'm saying that that derivative is this quantity. Most of you would get that. If you don't get it, let's try to see how we get it. So give me a couple of minutes while I write a few things on the slide. Okay. So I am ready now. I want to explain how I went from here to here, right? So let's first understand how did we compute A3. This is what our formula for A3 was. It was the weighted sum of the inputs plus the bias vector, right? So it was just I took this as the input, this red guy is as the input, which is the entire H2 vector, then multiplied them by the weights, which was W3, and then added the biases, which was B3, right? So that's what this formula is capturing. Now I have just expanded that formula. I have taken the case where I have only two neurons in the output layer. That's why I have only A31 and A32, and I have 3 neurons in the previous hidden layer. That's why I have H21, H22, H23. So this weight matrix would then be a 2 cross 3 matrix multiplied by a 3 cross 1 vector, and the biases, I would have just 2 biases corresponding to the 2 output neurons. So I have this 2 biases, right? So that's how this computation is. Now let's write down one of these guys, right? So A31 is, what is that equal to? W311. I'm just going to do the multiplication. Into H21 plus W312 into H22 plus W313 into H23 plus the bias term, which was B31. Okay. Now what are the indices here? This is I plus 1, right? So I plus 1 is equal to 3. This is my m, right? Because I am trying to take the derivative of ai plus 1 comma m with respect to h I j, right? So my I plus 1 is equal to 3 and my m is 1 in this case, and of course my I would be 2 in that case, right? Okay, so my I is 2. Now what is my j? I had taken the specific case of H22, so my j is equal to 2, right? So now suppose I want to take the derivative of this quantity, which I'll write here, derivative of A31 with respect to H22, okay, where this is I, this is j, and this is m, okay. Now what would that be? I have written the expanded formula of A31 and I am taking the derivative with respect to H22. So this will disappear because this does not depend on H22, this will also disappear, this will also disappear. So what will remain is W312 into H22, and the derivative of that with respect to H22 would just be W312. And what is W312? What are these indices? 3 is actually equal to I plus 1, okay, 1 is coming from the m, and this 2 is coming from the j, right. So that's what I get, Wi plus 1 m j, right. So this is the mjth entry of the Wi plus 1 matrix. In this case it is the 2, 2 entry of W3, okay. So that's how you should read this. So I hope this is clear now. We will move ahead. So this we had already computed in the previous lecture, and this we just proved why this is equal to this, right. So am I done here? Not quite yet. So let's spend some more time on this. So now suppose I have this vector, right. What is this vector? This is the derivative of the loss function with respect to the layer I plus 1. This is how I will write it. It will be a collection of the partial derivatives. So in this case, since I plus 1 is equal to L, I have k elements here. So I have the derivative of the loss function with respect to the first neuron in the output layer, with respect to the second neuron in the output layer, third neuron, all the way up to kth neuron, right. And now what is this? Wi plus 1. So I had the W3 matrix, okay, and this dot here means here I should have had the row index. Instead of the row index, I have a dot here. That means I don't care about the row. I am going to take all the rows, and all the rows from which column? The jth column, right. So that is what this notation means. I have the W3 matrix. I am going to take all the rows of that matrix because I have not specified an index for the row, but I have specified an index for the column. So that means I am taking all the rows for the jth column, which is the same as taking the entire jth column, right. So how would I write that matrix? This is how I will write it. This is W3, the first row jth column, second row jth column, all the way up to kth row jth column, right. So these are two matrices that I have. Now if, sorry, these are two vectors that I have. I have still not shown why I came from here to here, right? That will become clear in a while. Why did I start discussing about these two? Just assume that these two are the vectors given to you, right? Now, what is the dot product of these two vectors going to be? I am going to take the dot product of these two vectors. So, it is going to be this multiplied by this multiplied by this, all the way up to this multiplied by this, and the summation of those, right. So, there are going to be k terms in the summation, and every term in the summation is going to look like the product of these two quantities, right. So, this quantity that you have here is essentially the dot product between the jth column of the w of the weight vector and this gradient vector which you had already computed, right. So, that is all it says. This is the same formula that I have here, and again this is not very difficult, right. So, even if you did not get it now, you could just go back and take a look at the slides. All the notations have been explained clearly. If you understand the notations, this is a straightforward leap from there, right. So, whatever we had computed, what am I trying to say, what is my summary? I have computed the derivative of the loss function with respect to one of the hidden units, right. I wanted to, in fact, not even this, right, just one, the dark red guy, right. I actually wanted to compute the derivative with respect to entire H2, but I have just computed with one element of H2, right, and that is this quantity. It is the dot product between two vectors. One of the vectors is the jth column, right, and j comes from here, the jth column of the weight matrix, and the gradient vector, right. The gradient vector is the what we had already computed earlier. Okay, so where do I go from here? I have the formula for one of these guys. I want the formula for all of these guys, right. I want now to compute the derivative of the loss function with respect to any hidden layer hi. Okay, so what will it be? It will just be the collection of the partial derivatives with respect to all elements of that hidden layer, which is hi1, hi2 all the way up to hin, and I just know the formula for one of these guys, right, hij. So, I can just substitute the value of hi of I and j accordingly. So, I will keep the I as it is because I have I here, and wherever I see a j, I am going to substitute 1, 2, 3 all the way up to n, right. So, this is what it is going to look like. It is the dot product between the first column of the weight matrix with the gradient vector, the dot product of the second column of the weight matrix with respect to the gradient vector, the dot product of the last column of the weight matrix with respect to the gradient vector, right. So, what is that looking like? This is the so let me just try to write the matrix W transpose, right, W I plus 1 transpose. So, this would be the first column of Wi plus 1. This would be the second column of Wi plus 1 all the way up to the nth column of Wi plus 1. Remember, I am writing the transpose, hence I am drawing rows but saying columns of Wi plus 1, and all of these is getting multiplied by this gradient vector, right, this gradient vector, right. So, essentially what I am doing is that every element of this vector is essentially the product of one row of the matrix with this gradient vector, right. So, now I can write it even more compactly. I can just write it as the product between the matrix W transpose and the gradient vector, right. That is what I have shown here, because the first element of the resulting product is going to be the dot product between the first row of this matrix and the gradient vector, the second row of this matrix and the gradient vector, the third row of this matrix and the gradient vector, and I can write this entire thing as just very compactly as a matrix vector computation, and this is what I have done here, right. Again, if you are confident with your linear algebra, if not, there is a separate set of lectures that I put out on linear algebra, you can go and look at them, but this I am sure most of you would be aware of, right. So, I have taken the matrix and I could write the entire gradient. Now, this is the gradient of the loss function with respect to the hidden unit hi, which I can just compute as this. And why am I confident of computing this? This I already know, right. Whatever are my current weights, what is the current W3 matrix looking like, whatever it looks like, I just have to take that. And this I already computed in the previous lecture. This was the gradient of the loss function with respect to the last layer, right, because here I is equal to 2, so I plus 1 is equal to 3. But now I have a problem, right, I have a slight problem here. What is my problem? Now, suppose this was derivative of the loss function with respect to h1, right. So then what would this have been? So I is equal to 1 now, so I'll just substitute this. This would just be W2 transpose. This is not a problem for me. I know the weight vector. Whatever is the weight vector, I'll use that. But this would have been derivative of A2 with respect to loss function, right? That means this guy. And this I have not computed yet, right? So if I compute this, if I have a generic formula for computing this, I already have a generic formula for computing the derivative of the loss function with respect to hi, right? If I have a generic formula for computing the derivative of the loss function with respect to any ai, then I am done, right? Because if I have any ai that I could be 1, I could be 2, I could be 3, I can just substitute it here depending on which hi I am dealing with, right? So I have not done that yet. I have only done for the spatial case when I is equal to L, right, the last layer. So this part I need to do now. So that is what I am going to work on. So this is what I said, right? I don't know how to compute this quantity when I is less than L minus 1, right? That means I have only done this, I have not done these two guys here, right? So let's see how to compute that, and that's going to be again easy. So this is what this looks like. So I already know how to compute the derivative with respect to each of these guys, right? Now I want the derivative of the loss function with respect to this. So again I am going to do the same thing. I am trying to compute the derivative with respect to one of the elements here, okay? And what would that be? That would be the derivative of the loss function. I have already computed till here, so then I can just use that part as it is, and then the derivative of hij with respect to aij, right? And remember that how did we compute the h's? So this is, suppose I look at h2, I had h21, h22, h23, and how did I compute that? I had computed that from the a vector, and there was a 1-to-1 correspondence, right? So h22 was just the g function applied to a22, h21 was just the g function applied to a21, and h23 was just the g function applied to a23. So if I am trying to compute the derivative of hij with respect to aij, it's just the derivative of this g function that I had used, right? So I am just trying to compute the derivative of this with respect to aij. So I am just going to call that as g dash, right? Because it could be any function, but I am just taking the derivative. So this is what it looks like. This guy I have already computed. This is just g dash aij, right? So now again from this one element, let me go to the entire vector. So now I want the derivative of the loss function with respect to ai, the entire vector. So it is again going to be a collection of the partial derivatives, and every element I know how to compute. So I have a formula for aij. So now I will go from ai1 all the way up to ain. I will just substitute j equal to 1 to n everywhere in the formula, and this is what I get, right? So this is one vector that I have. I could think of this as another vector. This is not the dot product between two vectors, right? Because the dot product between two vectors gives me a scalar. This is the element wise multiplication between two vectors, right? This first vector is simply the gradient of the loss function with respect to h, and this second vector is just a collection of the derivatives of the activations with respect to pre-activations, right? So this element wise matrix multiplication, I can show it as this is called the Hadamard product. So I can just multiply every element of the first vector with every element of the second vector, and I'll get this quantity, right? So now I have computed ai theta, and let's see what it depends on, right? So it depends on the derivative of the loss function with respect to hi, right? So now let's see, if I wanted to compute the derivative of the loss function with respect to a2, then I should know the derivative of the loss function with respect to h2, and then I should know these g's. So I already know that. That is not a problem, right? Now suppose I wanted to compute the derivative of the loss function with respect to a1, then I need the derivative of the loss function with respect to h1. Do I know that? I know that because I had computed the previous formula, and the derivative of the loss function with respect to h1 depended on the derivative with respect to a2, and I just computed that, right? So I can just do it one by one at a time and keep going down the chain. So now I have the formula for computing the derivative of the loss function with respect to the pre-activation at any layer, with respect to the activation at any layer, and I just keep doing this one by one, and whenever I want to compute something, everything that I need for that is already computed, right? I'll just explain that intuition again. So I started by computing the derivative of the loss function with respect to A3, right? That was the first thing that I did, and there was nothing special about A3, right? It was the activation at the output layer. Now when I want to compute this, okay, let me just do this on the previous slide maybe. Yeah. So I started by computing the derivative of the loss function with respect to A3. So this I had already done, right? Then I wanted to compute the derivative of the loss function with respect to H2, and I was all set because I need W3 for that, and I need the derivative of the loss function with respect to A3, which I had already computed, right? So I am ready to compute derivative of H2. So this part is done. I have now been able to compute this. Then I wanted to compute the derivative of A2 with respect to the loss function, and the formula on the next slide, I'll just go to the next slide now. The formula on the next slide says that the derivative of loss function with respect to A2 just depends on H2 and some quantity, right, which is easy to compute, right. This G prime is easy to compute and we will compute it at the end, right. For now, just convince yourself because it's a simple function, right. Suppose my my activation function was the sigmoid function, then I have 1 over 1 plus e raised to minus A22, right. H22 is equal to 1 over e raised to 1 over 1 plus e raised to minus A22, and if I want to compute the derivative of H22 with respect to A22, I can do that, right. I can apply the UV rule and keep going and I will be able to get it, right. So this quantity is easy to compute, okay. So that's why I am not worrying about that. Yeah. But apart from that, it only depends on derivative of H2, and that we just computed on the previous slide, right. So I have everything that I want till this point. Then again, I want to compute the derivative of the loss function with respect to H1, and I know for that I just need the derivative of the loss function with respect to H2 and I need W2. These were the two quantities involved, and I have that because I just sorry, not H2. A2 and W2, right. So these are the two quantities that I need for computing derivative of the loss function with respect to H1, and I just computed that. Now I want to compute the derivative of the loss function with respect to A1. So for that, the the quantities that I need is the derivative of the loss function with respect to H1, right. And apart from that, I need this simple quantity which I just showed is easy to compute, right. So that's, if I just keep going one by one, at every stage I have all the quantities that I wanted to want at that stage for computing the quantity of interest, right. So now at this point you should be convinced that we have a generic formula for computing the derivative of the loss function with respect to the hidden layer, no matter where the hidden layer is. It's first hidden layer, second, third, fourth, everyone we have this formula. So we are almost done, and now we'll reach to the final part in our chain rule. So let's look at that in the next module.